Hi everybody, and we continue discussion of collisions, elastic and inelastic collisions. And last time we discussed absolutely a perfectly elastic collision, how it looks in the laboratory reference frame and also in the center of mass reference frame. And we understood that in the center of mass reference frame, the total momentum of two particles is zero. And the total momentum of two particles is the momentum of the first particle plus the vector of momentum of the second particle, and that is the zero in the center of mass reference frame. That is the, I would like to call it C reference frame. From here we immediately obtain that P1 should equal to minus P2. That is, the momentum of the first particle equals in magnitude and is oppositely directed with the momentum of the second particle. That is with respect to the center of mass. And it means that the two momenta can be depicted like this. P1, and this is the momentum of P2. Two particles which have masses m1 and m2 collide, and they have equal momenta in the center of mass reference frame. In this reference frame, this point C, which is the center of mass or the center of inertia, this point is at rest. Its velocity is zero in the reference frame associated with the center of mass. If two momenta are equal before the collision, the same will be true after the collision, because when particles are colliding, only internal forces act between them and no external forces should be taken into account. So in this particular case, law of conservation of momentum holds, and total momentum of the system before the collision should equal the total momentum of the system after the collision. So after the collision, the same will be true, and if we denote what happens after the collision as P1 prime, then it will be equal to P2 prime after the collision, the same as before the collision. And if we use the law of conservation of energy, which is applicable in for absolutely elastic, perfectly elastic collision, then due to conservation of energy, we obtained last time that the momentum of the first particle does not change in magnitude. It changes only in direction due to collision. So we can write that P1, the momentum of the first particle, the length of this vector, or the magnitude of this vector, equals the momentum of the first particle after the collision. Therefore, the momentum is m mass times velocity, and magnitude equals mass times mass 1 times velocity 1 after the collision. So we obtain that the velocity, the magnitude of velocity does not change in collision. And it means that if we draw the velocity of the first, if we show the vector of velocity of the first particle before collision, then after collision, this vector will somehow change its direction, but not the length of the vector. The magnitude will remain the same. It means that after the collision, the end of this vector may belong to some circle, to some circumference. And this is the center of mass. After the collision, the velocity of the first particle may remain the same, but it most probably, because of collision, it will be directed in some different direction. It will show somewhere, for example, here, after the collision. After the collision, it will be vector prime. It will be turned by some angle beta. And the length of this vector will remain the same. So in many, many collisions, these vectors will show in different directions, and all of them will, the end of this vector will belong to this circumference with the radius of this circle equal to v1, the velocity of the first particle before the collision. I repeat that all this is true in the center of mass reference frame. In any other reference frame, the situation will be different. In the center of mass reference frame, the vector velocity of the first bombarding particle after the collision, or as a result of collision, will just turn at some angle beta and will not change its length. The length will remain the same. So any vector of velocity of the first particle will belong to this circumference. Will start in the center C, and the end of the vector will be somewhere here. So all possible vectors may look like this. All possible vectors as a result of collision. That's very simple, and that's in the reference frame associated with the center of mass. But we are mostly interested in what happens in a laboratory reference frame related to the ground. So in order to consider the same situation in a different reference frame, we have somehow to transfer from the first reference frame to another reference frame. And how to do it, we discussed it. If we have two different reference frames, one is O and another is O prime, then, and we have some point that is particle M1, and this point has a radius vector r in the first reference frame, and it's characterized by a different radius vector r. The notation is not correct because I was using prime as the velocity after. Here, I don't remember what was my notation last time during the last lecture, but now I denoted prime as the velocity after the collision. So this should not be a prime, but, well, some other after the collision, or the radius vector in a different reference frame. Well, let it be a radius vector tilde, r tilde. And the second reference frame is characterized by radius vector r with respect to the first reference frame. Then, from this triangle of vectors, we may derive that r equals capital R plus small r tilde, that is in a different reference frame. If we differentiate it with respect to time, we obtain the relationship between velocities. That is, the first term will be the velocity of this mass with respect to the first reference frame, then the velocity of the second reference frame, capital V, with respect to the first, and then the vector velocity with respect to the second reference frame. So if we have the second reference frame coinciding with the center of mass of the system, with this point, let the second reference frame coincide with the center of mass. Then that will be the velocity of the center of mass. And so we understand that if we know the velocity of a particle in the second reference frame, and we want to know the velocity of the same particle in the first reference frame, then we have just to add the velocity of the center of mass to this velocity in the second reference frame, and then we will obtain the velocity in another reference frame. Very simple formula. So in order to move from this picture to another, a different picture of vectors, related to the laboratory reference frame, we have to add this vector to each other vector here, whatever vector we have. Whatever vector we have in the second reference frame, we must add the velocity of the center of mass in order to obtain the velocity of the same particle in the laboratory reference frame. So how to add vectors we know very well. For example, how to add a vector to this vector v1. We have to draw the vector which is the velocity of the center of mass here, and that will be that vector. I show it here separately. That will be the velocity of the first particle in the first reference frame, and this is in the reference frame associated with well, again, it's a mess with notations. I'm sorry. I started denoting with a prime vector after the collision. That is after the collision. That is before collision and after collision. But all these vectors refer to the reference frame C. That is center of mass reference frame. So in order not to confuse different vectors, let us add index C, so that this vector of velocity is measured with respect to the center of mass reference frame. Center of mass. And so this is the velocity of the first particle in the laboratory reference frame with respect to the ground. And this is the velocity of the same particle with respect to the center of mass. And this is the velocity of the center of mass with respect to the ground. Just three vectors. It's very difficult to be confused here, but just three vectors. The velocity of the particle with respect to the ground, the velocity of the center of mass with respect to the ground, and that is the velocity of the same particle with respect to the center of mass. That's it. So the same is true as far as the velocity of the particle is concerned after the collision. After the collision, the vector of the velocity is just turned by some angle beta in the C reference frame related to the center of mass. But what will happen to this velocity, to this velocity now, after the collision in the laboratory reference frame? This is the laboratory, the velocity with respect to the laboratory reference frame. What will happen to this vector? Well, the same formula, the same logic. To the initial vector we add vector VC. VC should be added to this vector we have to find the sum of these two vectors. One is the velocity of the center of mass, and another is the velocity of the particle in the C reference frame after the collision. So the result will be this sum of two vectors. That is the velocity of the first particle after the collision. I denoted it by prime. The velocity of the particle after collision in the laboratory reference frame. According to this formula, I have to find it as the sum of two vectors, 1 and 2. Two vectors. So, as far as I understand, last time we had no time to show what is this angle, the angle of deflection of the bombarding particle. The maximum angle of deflection will be this one, when this is the right angle, and then the maximum possible angle alpha maximum, will be found as sine alpha maximum equal to what? If this is the right triangle, then the opposite leg should be divided by this hypotenuse. The hypotenuse is clear. This is the magnitude of the velocity of the center of mass. This is the hypotenuse. And the opposite leg is what? It's the radius of this circle. And the radius is the initial velocity of the first particle in the C reference frame. in magnitude, that is the same as the final velocity after the collision of the first particle. But it's convenient to use this quantity because this is the radius of the circle, the same as this, the same length as this radius. So in the nominator we will have the velocity of the first particle in the C reference frame, the magnitude of this vector, divided by the velocity of the center of mass. Last time we derived all the formulas for these two quantities. You remember the formulas are not complicated. I will repeat these formulas here. That will be m2 v1 m2 v1 divided by m1 plus m2, and the denominator, that is the velocity of the center of mass, will be m1 v1 divided by m1 plus m2. We obtained these formulas last time. I will not waste my time now to derive them again. We derived these formulas from the law of conservation of momentum. Well, do you have these formulas in your notes? I think you do. You must have these formulas. You do have these formulas. So after we substitute these formulas here, we will obtain that that will be m2 divided by m1. So the maximum angle of deflection of the bombarding particle measured in the laboratory reference frame, the bombarding particle was moving here in this direction. That was its velocity, this whole vector. And then after the collision, the vector turned by maximum possible angle. It's not necessarily maximum in every collision. In some collisions, it will be less than maximum, like this one or like this one. But the maximum possible angle will be determined by this ratio of masses, m2 over m1, the masses of two particles. And here we may describe three different situations. First situation, when the mass m1 is larger than m2. In this case, if the denominator is larger than the nominator, then this expression will be less than unity, And so there will be some angle, well, just like shown in this picture, some angle corresponding to a sign which is less than unity. In this case, the possible angles of deflection alpha will be between will be larger than minus alpha maximum and smaller than alpha maximum. So all the deflection angles will belong to this range of angles, the minus alpha maximum and between minus and plus alpha maximum. Another situation is when m1 equals m2. In this case, we will obtain that the sign of alpha maximum is unity. It means that alpha maximum is 90 degrees. That will happen when the beginning of this vector v1 will coincide with the circumference. This point will be here. Then the maximum angle of deflection will be 90 degrees. And that's obvious from the picture. If this point A, for example, coincides with this point B, then the maximum angle of deflection will be between plus 90 degrees and minus 90 degrees. maximum angle will be plus minus 90 degrees. And actual angle of deflection will be between minus 90 degrees and plus 90 degrees. And there is another interesting situation when m1 is less than m2. That is, a light bombarding particle collides with heavy particle. It's obvious physically, on the level of intuition, it's understandable that if light particle collides with heavy particle, then heavy particle may practically remain where it was, and the light particle may just rebound and fly in opposite direction. So in this case, any angles are possible, any angles of deflection of bombarding particle. And we see from this formula that if m1 is smaller than m2, then this expression will give you something larger than unity. And the sign alpha will be larger than unity. It means that this formula will not give you a correct answer, but it's obvious that in this case point A will belong to this area, will be inside the circle. This point will be inside the circle, so that any angle of deflection is possible. Any angle of deflection. By the way, if m1 is smaller than m2, then in this case, look here at this formula. If m1 is smaller than m2, then the velocity of the center of mass will be smaller than the velocity of the first particle in the C reference frame. Smaller, will be smaller. Vc, the velocity Vc, is smaller than this velocity. So that the beginning of this vector Vc will be somewhere here inside the circle, and that will be the small vector. And the formulas show that the length of this vector will be less than the radius of this circle. So this will be the small velocity of the center of mass, because the second particle is heavy, it's a large particle, and it's at rest. It's not moving, so the center of mass practically doesn't move in this case. And then the possible angles of deflection will be from 180 degrees and minus 180. From minus 180 to plus 180. So this particle can be deflected by any angle, small angles and large angles, and 90 degrees and more than 90 degrees and even 180 degrees. That's the angle of deflection. It's when the light particle impinges against the heavy particle and recoils backward. Then it will go backward, and the scattering angle will be 180 degrees. So the physics of perfectly elastic collision is not complicated. All the formulas are simple, and the conclusions and the results are, well, intuitively understandable. That's understandable, that when the particle is heavy, the bombarding particle is heavy, it may be deflected by some angle which is not larger than the maximum possible angle, because the heavy particle may not be deflected very, very strongly by a light particle. But the light particle may be scattered at any angle by a heavy particle. Any questions? I would like to consider some problems from your home assignment. And first, first let it be problem number 163. So problem number 163. A body of mass m with a small disk of mass small m, also given the small m, is placed on the small disk placed on it. I will draw a picture. Here the picture is this. So the body is this, of mass capital M, and the small disk of mass small m is here. And this body rests on a horizontal surface without friction, and the disk is set in motion in the horizontal direction with velocity v. So the initial velocity is also given. The initial velocity is given of the small disk. To what height relative to the initial level will the disk rise after breaking off the body M? The friction is assumed to be absent. So the small disk, the small body, small m, is set to move at velocity v. Obviously, this small disk without friction will go along this curved surface, and it will somehow fly upward. And we need to find the height at which the small body will go up in this situation. So the small body will go up. And when the small body moves here along the curved surface, this small body will be accelerated, so there will be a force acting on the small body from the surface. And according to Newton's third law, the same force will act on the large body of capital M, mass capital M. So the large body which is without friction, which is placed on a table without friction, the large body will certainly move after that with some velocity u, because the small body is here accelerated. So that when the small body goes up, it will not go exactly upward. It will have some vertical component of its velocity, but actually it will have also a horizontal component of the velocity coinciding with the velocity of the large body. When the small body goes along this vertical wall, the velocity, the horizontal component of the velocity of small body will coincide with the horizontal component of the velocity of large body. So that the actual velocity of the small body will be directed somewhat at some angle to horizon. Angle to horizontal. Is it clear why it happens in this way? Why it goes in this way? There is, if this small body goes along a curved trajectory, then it will be accelerated, and any acceleration is caused by a force. So here will be a force of interaction between the small body and the large body. And this force of interaction will push this large body, and it will move at some velocity u finally. And so the small body will not fly vertically. It will go at some angle so that the horizontal component of its velocity will coincide with the horizontal component of the velocity of the large body. That's the physics. Now we have to use some laws of physics to solve this problem and to find the maximum height at which the small body will rise after leaving the large body. Well, first of all, we note that there are only internal forces in this system of two bodies, only internal forces acting between them, no external forces. And it means that the law of conservation of momentum holds. The initial momentum, mv, will be equal to final momentum of the system. The initial momentum, because initially this body was set in motion by some external actor. We don't care who or how it happened. We know that initially this body was moving at the velocity mv. So the initial momentum of the system of bodies was mv. And only internal forces act between these two bodies. So the law of conservation of momentum should apply here. Initial momentum must equal the final momentum. And final momentum will include the velocity of motion of the large body, that will be capital mu, plus the horizontal component of motion of the small body, small mu, the same horizontal component as for the large body. From here, we certainly may find this unknown velocity u of motion. That will be mv divided by capital M plus small m. That will be the horizontal velocity, a horizontal component. In order to find the height of the small body, we must use some other law of physics, obviously a law of conservation of energy. And mechanical energy here will be conserved because we know that there are no friction forces acting here, neither at this surface nor at this curved surface. There are no forces of friction. If we have no forces of friction, then we know the mechanical energy is conserved. So that the initial mechanical energy in this process must equal the final mechanical energy. What is final? Well, at any point, final point is arbitrary because the energy is conserved, it's conserved continuously all the time, and we may choose any moment in time as the final point. But we choose what is convenient for us. We will choose the final point we will choose the final point, the maximum height of motion of the small body. The final energy will be small body mass mgh. That will be the final potential energy of the small body. Also, at this moment of time, small body will have, certainly if it's the maximum height, then at this moment of time, vertical velocity will be 0. But horizontal velocity will not be 0. So there will be some energy associated with horizontal velocity, mu² over 2. And also there will be some kinetic energy of the large body, again mu squared over 2. That is the final energy of the system. I start from the final point. Final energy is the kinetic energy of the large body plus kinetic energy of the small body. It's present there because the small body has some horizontal component of velocity, and potential energy of the small body, depending on the height of its trajectory. At this point, vertical velocity of the small body is 0, so we don't have to take into account this vertical component of velocity. That's the final mechanical energy of the system. And what is the initial mechanical energy? At the initial moment, the mechanical energy will be determined only by the energy of the small body, because the large body was not moving in the beginning. Only the small body was moving at the velocity small v. That's the energy balance in this problem. That's the initial velocity, initial energy, initial mechanical energy in the system. It must be equal to final mechanical energy. The mechanical energy is conserved because there are no forces of friction. Okay. We already know this velocity u. We have found it from the law of conservation of momentum. So this quantity, this physical quantity is known, and v is known. The only unknown quantity in this equation is the height. The height h is the only unknown thing. Okay, it's not difficult to find h. Let's do it this way. It will be mv squared over 2 minus all these things. What is u squared? U squared can be immediately written as mv squared divided by capital M plus small m squared. So that is the square of velocity u. And then we will have here small m over 2 plus capital M over 2. Is everything correct? Seems to be so. Mv squared minus these two terms, and the velocity u is taken from this expression. So it may be somehow expressed in somewhat different way. That will be m plus m squared, and here I will have also m plus capital M. So that will be mv squared over 2, mv squared divided by 2, and m plus m will cancel, and only 1 m plus m will remain in denominator. And to continue this calculation, I will write that this is mv squared over 2 minus, oh no, I will do it in a different way. V squared over 2 will be a factor in this expression because it enters the first term and the second term, v squared over 2. I can take it out of the brackets as a factor, and in the brackets I will have small mass minus small mass squared divided by capital M plus small m. And that will be, when I make these calculations here, I will find capital M, small m, and small m squared and minus small m squared and capital M plus small m. That's the meaning of these square brackets. Capital M times small m and small m squared will cancel. That's correct. And what remains here is v squared divided by 2. And now after that, it's not a problem to find h. We have to divide by small m g. Small m will cancel, and it will be something like capital M v squared divided by g h capital M plus small m. That's the final answer. To this problem. Is it correct? Yeah. H is not here, sure. H should not be here. We divide it by small mg, and h remains here. So small m cancelled. 2. Another 2 is here. Yeah.
In the problem said that with respect to the original height, so we shouldn't take into account the height of m and mass m, because the value first is at one level and then goes up and then goes more up.
Yes, it goes up. First it goes up here and then goes up to a larger height. And what we have to calculate the height with respect to the initial level. So we need to calculate this height with respect to the initial level. And that's correct. mgh will be the potential energy of small body with respect to this level. The level of large body will not change, so that's correct, mgh. Small m cancels, divided by 2, divided by g. That seems to be correct. Well, so we have obtained the answer. We believe that this is the final answer. Why do we believe so? Why do we think that that is the final answer? Because all the quantities in this formula are given in the statement of the problem. Everything is given. The masses, the velocity is given. Acceleration of free fall is always given. So this formula contains no unknown quantities. All the quantities are given in the problem. That's the indication, the first indication that we have obtained the final answer. Now we have to check this answer. How to check it? First, we check the dimensions, the units of measurement. The units of measurement of mass will cancel. Kilograms and kilograms will cancel. And here we will have meter squared, velocity squared, meters over second squared. And acceleration of free fall will be meters by second squared. So after all cancelled, we obtain meters. So this formula gives meters. That's what we need to have to measure the height. The height should be measured in meters. And the formula is correct as far as the units of measurement are concerned. What about the physical sense or physical meaning of this formula? Let's consider it in this way. Suppose that the large body is taken larger and larger and larger so that the capital M goes to infinity. Capital M is much, much larger than the small m. Then small m can be neglected here in comparison with capital M. And then two capital M's will cancel. And we will have the formula that is the second way to test the answer. We will obtain such formula v squared equals 2gh, which is the consequence of the law of conservation of energy, mv squared over 2 equals mgh. Potential energy equals the initial energy. Potential energy equals the initial kinetic energy of the particle. So that's quite reasonable. If the large body is very large, then it will not influence at all the answer. And that's natural, that's understandable on intuitive level. Well, we may check the meaning of other relationships here. For example, how should the height depend on the velocity? It's obvious that the initial velocity, the smaller the initial velocity, the smaller will be the height. They should be somehow proportional. The height and the velocity should be in this relationship. That's clear, that's good. And what about the mass of the relationship between the masses? What if the small body is much heavier than the capital M? Small m is much larger than the capital M. Then capital M is very small. Let it be very small, very light body, large but very light with very small m. What happens then? This formula will give us that m can be neglected here, but m stands here as a coefficient. So the smaller the m, the smaller will be the height. And that's quite natural, that's understandable. If this mass is very small, then this body will not go far into the sky, because all its energy will remain, all its momentum will remain, and it will just go with the initial velocity v, and the height will be very small. It will not even break off this surface. If the mass tends to 0, then this small body will be unable to jump up. That's also clear, that's obvious. So the formula obtained satisfies all the criteria. It has the correct units of measurement, correct dimension, and it provides a reasonable sense, reasonable physical meaning. So it seems to be correct. In this way, you should analyze. Okay, what's the question?
If the mass of the large body is big enough, that means the body will go horizontal up or still go like
If which mass is
the large body?
The large body is small. If it's very big, we considered this situation here at this point. When capital mass is very large, then small mass may be neglected here, and capital M will cancel, and the height will depend only on the initial velocity. We considered this situation. So first we allowed this capital M to go to infinity and analyzed the formula. Then we allowed small m to go to infinity and again analyzed the formula. Then we allowed for the velocity to increase or decrease and analyzed the formula. And each time what the formula gives you should coincide with your intuition, with your intuitive understanding of this situation. Any more questions? Okay, next I wanted to consider problem number 164. Problem 164. Again, we have to draw a sketch of what happens here to depict the situation. So a small disk of mass m, this small body, slides down a smooth hill of height h without initial velocity and gets onto a plank of mass capital M. This is the plank of capital M. And the plank lies on the horizontal plane at the base of the hill. Due to friction between the disk and the plank, so here there is some friction. There are forces of friction here. When the disk is here, there are forces of friction between the disk and the plank. And due to friction between the disk and the disk slows down and, beginning with a certain moment, moves in one piece with the plank. So the plank can move on the horizontal surface without friction, but there is a friction between the disk, between this body and the plank, and no friction in other places. Only here, only on this surface, there is friction. So when the disk comes here and enters the surface of the plank, there are forces of friction acting on the disk and equal forces of friction acting on the plank, so that the plank starts moving, and finally we will have something like this. The plank moves together with the disk on it, because there are forces of friction between the disk and the plank. So this is the plank, which will start moving along the horizontal surface. Find the total work performed by the forces of friction in this process. That is the first question. Total work of forces of friction performed by forces of friction. And the second question, can it be stated that the result obtained does not depend on the choice of the reference frame? We will discuss it later. So first of all, we have to find work of the forces of friction. So we have to apply some laws of physics which are pertinent to this situation, which are applicable to this situation. If this disk slides down without friction, then we can easily find the final velocity. But we don't actually need this velocity, because we know that this kinetic energy of the disk will be equal to the initial potential energy of the disk. What we need is the initial potential energy, and we know very well the initial potential energy is mgh for a body of mass m at the height h. And this initial potential energy will somehow be spent on increasing the energy of the plank, because it will move and it has some mass, and it will have some velocity u. And also, so the initial potential energy will be spent on several processes. First, the kinetic energy of the plank and the disk on it. Final velocities, there will be some final velocity, so finally the system of bodies will possess some kinetic energy. And also some portion of work, some portion of the initial potential energy will be lost on friction, on work against forces of friction. So some part of this energy will go to forces of friction, will be spent on the work against forces of friction, and another part of the same potential energy will be finally transferred into a kinetic energy of the whole system. So the energy relationship must be something like that. Initial energy mgh will be transferred to a final kinetic energy of the system of bodies. A small disk of small m and capital M will move at some velocity u squared, mass times velocity squared over 2. That is the final kinetic energy of the whole system. And also a part of this initial potential energy will go to perform, will be spent on work against friction, forces of friction. It's not difficult to find A from this equation, but we know for this purpose we must know the velocity u, the final velocity u of this system. And this velocity can be found from the law of conservation of momentum, because if we know the initial velocity v and the mass, then the momentum of this system will be mv, the momentum of this disk before it enters the surface of the plank. And this initial momentum will be transformed finally to a final momentum of the whole system, small m plus capital M, moving with velocity u. Because when the disk is interacting with this plank, it moves on the surface of the plank and it decelerates because forces of friction decelerate it. But the plank is accelerating because the same forces of friction act on the plank. But these forces of friction are internal forces in the system of two bodies, and no other external forces act on this system. Or, in this particular case, the action of external forces balance, all the external forces balance each other. That is the force of gravity and the force of reaction of the table surface. These two forces balance each other. So the external forces may be considered as absent here. Only internal forces are important, the forces of interaction between the small disk and the plank of mass capital M. If you have a closed system of bodies with only the internal forces acting, then the law of conservation of momentum holds. Law of conservation of momentum can be applied here, regardless of the fact that there are forces of friction, because forces of friction are internal forces in this case, and internal forces do not prohibit the law of conservation of momentum. So in this case, we must use this law, the initial momentum, which is all stored in the small disk, and the final momentum of the disk when the disk has stopped on the surface and moves as one piece together with the plank. Then both masses will have this final velocity u. In this case, we have to know the velocity v, which can be calculated very easily because mv squared over 2 equals mgh. And that's true because here on this surface there is no friction. There is no friction and the energy is not lost on friction. So the initial potential energy mgh all goes into a final kinetic energy of the disk here at this point. So the velocity v can easily be calculated. We know the velocity v, it's square root of 2gh. Then from here we obtain the velocity u. We need it because it's here in the first line. And the velocity u will be small m divided by capital M plus small m. And v, which is square root of 2gh. And then we take this expression and substitute it in the first equation and obtain the quantity A, which is required in this problem. A from the first equation will be mgh minus small m plus capital M over 2 times u squared. And the velocity u squared will be small m squared divided by m plus capital M squared, and 2gh square root vanishes because we take the velocity squared. So here again this will cancel. Only one component, small m plus capital M, will remain in denominator. So 2 also, this coefficient 2 will cancel, and gh can be taken out to factor the round bracket. And what will remain in the round bracket? Small m minus small m squared, small m here and minus small m here squared divided by small m plus capital M. And after simple calculations we will obtain gh. Small m squared will cancel with this squared, and then we will have small m, capital M, small m plus capital M. That's the work performed by forces of friction. And this amount of work can be measured because this work will go to increase the internal energy of these two bodies. And the increase in internal energy will mean that the temperature will rise. And we can measure this quantity if we know the heat capacity of these bodies, and if we measure the initial and final temperature, and we measure the rising temperature, and then we may measure, in this way we can measure this work of forces of friction. Is this formula correct from the point of view of dimensions? So we have kilograms squared in numerator divided by kilograms. So we will have kilograms times h times g. That is mgh. Yes, we know this is work by dimensions. This is measured in joules. So the units of measurement coincide with what we need. We need joules to measure work, and we obtain this. So as far as the units of measurement are concerned, the formula is correct. Then if we consider some relationship, the larger the h, the larger will be the work performed. That's natural. And if we play with masses, if mass, for example, if capital M is increased, infinitely increased, then the small m will be neglected here, can be neglected in the denominator, and capital M will cancel. And we will obtain that all the energy, mgh, all the initial potential energy of the small disk will be transferred to work against forces of friction. If capital M cancels here, when it's very large compared to small m, then this formula will give you mgh, and that is the potential energy. That's quite reasonable, because if the plank is very massive, is very hard, then the small body will hardly move it. The velocity will be very small, practically negligible, and all the initial potential energy will be transformed into forces against friction, into internal energy. And the final kinetic energy will be very small. If capital M goes to infinity, then the plank will not move, will not shift. Actually, it will remain in place at rest, so that all the energy will be transformed into internal energy. All the initial potential energy will go to increase the temperature. And that's what we obtain here, that if capital M goes to infinity, then this formula will give you mgh. That's quite natural, that's reasonable. So this formula works. It seems to be correct. It's good. So there is another small point which we must discuss here. That is when the small disk M moves on the surface of the plank, the forces of friction are applied to small disk from the surface of the plank, force of friction, and equal force of friction will be applied to the plank, and force of friction the same. So if you calculate work as the displacement times force, force times displacement, there are two possible ways to calculate it. You may take this force of friction, which is directed here, and multiply by displacement, and it will give you the positive work performed. But you may take this force of friction, which is directed oppositely, and multiply it by displacement, and that will give you negative work performed. So in this problem, it's also important to understand that that the total force, these two forces are equal in magnitude and oppositely directed according to Newton's third law. But these two forces are applied to different bodies. And so the work of which force do you need to calculate? That will give you different signs of the work. And there is another question: can it be stated that the result obtained, that is the work which we have found, the results obtained does not depend on the choice of the reference frame. Yes, it does not depend. It does not depend. Why? Because this work can be measured as the rise in temperature of the bodies. And the rise in temperature is the same for any observer who observes this process from any reference frame. Whatever reference frame you choose, either you stand still on the ground, or you move on a bicycle, or you move quickly in the car, you will see the same change in temperature. Any questions? We have some time to consider another problem. Well, and I would like to consider problem 157. A chain hangs on a thread and touches the surface of a table by its lower end. So there is a chain and it touches the table by its lower end. Show that after the thread, there is a thread on which the chain hangs. Show that after the thread has been burned through, the force exerted on the table by the falling part of the chain at any moment is twice as great as the force of pressure exerted by the part already resting on the table. So we need to find the force exerted on the table by a falling chain. So this thread is torn, it breaks or it's burned, and the chain starts falling down. The chain starts falling down, so that after some time, the upper end of the chain will go down by x as a function of time, and the chain will fall down, and some part of it will be on the table. On the table. The lower part of it will be on the table. So there will be some mass of the chain which is on the table, and this mass is at rest. It doesn't move, and it's a function of time because the chain falls down, and each small interval of time, more and more elements of this chain hit the table and remain at rest here on the surface of the table. So there is a mass which rests on the table, and this mass is changing in time. If the mass changes in time, we can use the Mizhersky equation for motion of a mass with variable, of a body with variable mass. The Mizhersky equation is, you remember, the mass dv dt equals f minus the velocity u dm dt. We derived this Mizhersky equation, and I wanted to repeat it and wanted to consider the problem to repeat this interesting equation, and we discussed it, and we know the meaning of each term. This is the mass here, And what is the acceleration of this mass, dv dt? The acceleration is 0 because this part of the chain rests on the table. Its velocity is 0 and its acceleration is 0. So this term will be 0 in this particular problem. This term will be 0. And what remains from the Mishchersky equation? That will be f dt equal to u dm. And what is u? U is the velocity with which the chain goes down. So that is exactly, u is exactly x dot as a function of time. But what is the x dot? Do we know this? The chain falls down with the acceleration of free fall, actually. It's falling down freely under the action of forces of gravity. So we know the acceleration. We know that the acceleration x2 dots is constant and it's equal to acceleration of free fall. The chain just falls down, and we are sure that it falls down with the acceleration of free fall, as any other object does in the gravity field. It falls down freely, if not hampered. It falls down freely with the acceleration of free fall. So, if we know x 2 dots, then we know the velocity, which will be gt. And that will be the velocity u, which must be substituted here in this equation. Also, we need to know the function m as a function of time. What is this part of the chain which lies on the table? This is the same part that was here, but now it's here on the table. So the part of the chain on the table, on the surface of the table, will have the mass which is proportional to x. The mass of the chain on the table will be proportional to x. X is the length already fallen on the table. So in order to find the coefficient of proportionality, x is measured in meters, for example. So we need to know the mass of the unit length of the chain. So it will be the mass of the chain divided by its length, total length, times x. That will be the mass of the unit length, for example, the mass of 1 centimeter of the chain, multiplied by the length of the chain, and that will give us the total mass of the chain, which is already on the table. And x as a function of time is simply, if we know the velocity x dot, then x as a function of time is known as gt squared over 2. You know all these formulas from the kinematics. This is the length of the chain which is on the table. On the table is the same length which is here, which is absent here, which has already fallen down. We don't need the mass. In this equation, we need dm divided by dt. That is, we need to calculate dm dt, and it's very simple to calculate it. It's very easy to differentiate it with respect to t. It will be capital M, the mass of the chain, divided by its length, gt. So in this equation we will find f equals u, we have found it, it equals gt times dm dt, which is written here. It will give you capital M over L, again gt. And that will give you M over L gt squared. That is the force as a function of time. The force acting on the table due to the chain falling down and the elements of chain which move with some velocity and they have some mass and they are stopped by the surface of the table, and in order to stop some massive body you need to apply force, and each small moment of time you stop some small mass, and so you have to act with a force from the table to this chain. And the chain already on the table has this mass, so its weight is mg, and we have to multiply it by g to understand, to obtain the total weight. That will be the total weight of that part of the chain which lies on the table, which is already on the table. So that will be capital M over L. We must multiply by g. That will be g squared t squared over 2. And comparing this force, which is exerted on the table by the part of the chain which is already on the table surface, comparing this force with another force which is needed to stop the elements of chain falling on the table, we may easily compare these two forces. For example, we can divide f of t by mg, divide this expression by this expression, and we will obtain that this is m over L will cancel, gt squared will cancel, and that will be equal to 2. That is at any moment of time. Note that the force F is a function of time, and it's increasing with time quadratically. At the initial moment when time t is 0, the force is 0, and then as time goes on, the force increases as time squared. So it increases sharply, parabolically with time. But at any moment of time, this force is just 2 times the mass, 2 times the weight of that part of the chain which is already on the table surface at any moment of time. So this mass of the chain which is on the table increases with time, and the force acting on the table from the falling part of the chain also increases in time, but these time dependencies are the same, so that the force acting on behalf of the falling chain is at any moment of time twice the force acting on the table from the part of the chain which is at rest. So we have found the solution of this problem, and I wanted to discuss it because it gives you a beautiful example of application of Michelsky equation in such a not very obvious situation. It's not a spaceship, it's not a space rocket. But anyway, the same equation works and allows you to solve the problem. Okay, there was a bell, so that's the end of the lecture. We may finish it, and the next time on Monday, if I'm not mistaken, a person will come here to our class to announce the results of competition of the question of choice reports. That will be next time on Monday. I don't know what are the results, but he will come and announce the results.